Swartz.
Josh Harder.
Tom Weeks.
Is that Taylor?
Taylor Van Vliet.
And we're looking at the bridge at Kenwood, Madison, which is currently a low overpass. It's a railroad bridge owned by I&O. As its current state, it's 12-foot clearance. It has a 2.5-foot deck. It is 94 years old, and it has several bad options on the bridge, including crumbling foundations, rusted through members. One of the big vices last quarter was trying to figure out whether the bridge is ready to be replaced or not. And we have decided that it is ready to be replaced within the next 1 to 10 years, based on the city inspection reports, which I have a copy of if you guys would like to see. The bridge actually scores a 42. Anywhere in between 50 or anywhere below 50 is available for state help, but since it's a privately owned bridge, it's not available for that. So that means basically that if it was a state bridge, it would be replaced. But since it's privately owned, it's going to sit there. Basically, in this model, you can see that the widest part in the bridge is 13'3", and that's at the northwest corner. And trucks can actually get through the bridge on that side sometimes, and on the other side, they'll hit. And that's where we've had a lot of accidents that was referred to last quarter. So we decided to redesign the bridge, and our first option was to try to get the deck thin enough. Right now we have a 2.5-foot deck, so we want to get the deck down to 1.5 foot, which would give us, 1 foot, which would give us, 1.5 foot, which would give us 13'6", which is the statutory height in Ohio. So we went ahead and tried this option, and we'll let Tom.
They said I couldn't put the calculations on the poster, so I made a PowerPoint instead. So basically, from the American Railway Engineering and Maintenance Right-of-Way Association Code, I think I got that right. Or read my name, we'll just call it from that. I got, go back.
That's the first.
Okay, yeah. Basically, I got these unit weights, and I was trying to, and I had to get them into be like uniform loads across the transverse beams. This is just the transverse beams, which is
These beams.
These ones going across the bottom here. And to do that, basically we had to know the transverse spacing, and because that determines the dead loads. You know, you have a transverse beam here, and then you have a bunch of gravel and whatever on top of it. So half of like L/2, all that distributed weight goes to each beam, and you have 2 of those, so it's just the spacing. Anyway, go to the next slide. Selected a beam W12 by 136, which I'll get to that later, how I did that. And that's 136 pounds per feet. The deck, 1/2-inch thickness is the minimum from the code. And I basically did the 1/2-inch, converted it on the spacing, transverse spacing. We chose 2 feet center to center, giving us a 40.83 pounds per feet. The rails, that's given in this little illustration. I just chose the heaviest one you could use. They're 135, 136 pounds per yard, which for our spacing, we just made those into point loads on top of the beam for 2 feet. So basically it's 2/3 of that 136, it's 90. Locations of the loads, I made the center line of the tracks, the center line of the bridge equal to each other. And the spacing between the rails is 56.5 inches. So you have a track at 6.5 feet going across the beam, 6.65 and 11.35. And go next one. The ballast, the minimum is 6 inches below the tie. The minimum ballast cover of the tie is 4 inches, so I just made it 10 inches all the way across. It's easier. And it's conservative, so it's okay. I just disregarded the space of the tie, and that gave us 10 inches times 2 feet, 200 pounds per feet. The ties, they give the unit weight of wood. I just took the dimensions, you can see them there. And I made distributed load 26.5. And it starts at 4.5 feet and ends at 13.5 feet. Live loads, this is from the code. Maximum axle weight, it's a Cooper load. The maximum axle weight was 80,000 pounds. Minimum axle spacing was 5 feet. So I used those just to get the largest one possible. And it's plugging into this code. Pretty much just plug and chug. You have the weight times the transverse spacing over the axle spacing. And that's applied at the top of, that's just the entire weight, then applied at the top of each rail. There are about 18.5 thousand pounds. And the locations are at 6.5, 6.5, and 11.35. Impact load is the percentage of the live load applied due to rocking and other forces. That's exactly what the code said. Basically, they just plug in this code. That's also into this equation from the code. And this is for distances under 80 feet, and ours is only, the beam's only 18 feet long. So it's about 40% times the live load. Give us that. Then applied at the top of each rail, it's just that over 2. And it's also 6.65 and 1.35 feet. Wind load, they gave a 300 pounds per linear foot applied on the train at 8 feet above the track. So I just used our spacing again. Got 600 pounds, made a moment at 8 feet, and divided by the distance between the tracks to give us a positive and negative force on each one. The total loading, we end up getting 403 for the dead loads, which I just made 400. And the point loads are the 90 pounds, which is ultimately isn't that important. Then I just made the point loads for the live loads about 26,000 pounds. So I found the maximum moment in the beam. It's about 190,000 pound-feet. We chose the strength of steel to be 70 KSI. That's a maximum you're allowed to use them for structural steel. There's 90 KSI, but that's only for bolts and stuff. Factor of safety for the code is about 2, so it's 0.55 of whatever the steel strength is. And just went ahead and calculated the section modulus needed. Then I went to the steel code, found a beam with similar. It's a little bigger, but it's good enough. The maximum deflection in the beam was 0.2 inches, and the code allows 1/360th of the beam length, which was 0.6.